we present animations of approximation algorithms for three closely related problems: the Fermat point, n-ellipses, and the min-sum cluster Voronoi diagram. In all cases, we use a box subdivision approach together with soft predicates based on interval arithmetic. Our problems have applications in facility location. My name is Martin Suderland, and this is joint work with Ioannis Mantas, Evanthea Papadopoulou, and Chi Yap. Given a cluster of points C, in this example of size 3, and an additional point P, then we can define the distance from P to C. We define this distance as a sum of distances from P to all cluster points. In the example, this would be the total length of the three dotted line segments, which sum up to a distance of roughly 1.2. If we move the point P along a line, we can see that the distance is first decreasing and then eventually starts increasing again. In general, this distance function defined in a plane is convex, and if the cluster points are not all collinear, then it has a unique minimum. This minimum is called the Fermat point. Finding the Fermat point is a geometric problem which dates back to the 17th century. The Euclidean Fermat point is a solution of polynomials of degree exponential in the number of cluster points. For this reason, approximations of the Fermat point are of interest. We illustrate our approximation algorithm for finding the Fermat point, an example for a cluster of size 10. Initially, we start with a box containing all cluster points, because the Fermat point is guaranteed to be in the convex hull of these. We then split the box into 4 subboxes and decide for each if the subbox might contain the Fermat point. If we can be sure that the box does not contain the Fermat point, then we can discard it from further consideration and color it red. If we are not sure about a box, then we color it green, split it, and recursively study its subboxes later during the algorithm. The test to classify the boxes is based on an approximation of the gradient of the Fermat distance function for all points within a given box. In the example, the cluster points are intuitively speaking well separated, and boxes which do not contain the Fermat point can quickly be discarded. When the area of green boxes becomes small enough, then we can return an approximation of the Fermat point, here colored in blue. Here we have another example, which we consider a difficult instance for our approximation algorithm. The cluster points are almost on a common line, a line from the bottom left to the top right corner. This implies that the distance function restricted to that line is very flat. The approximation algorithm needs to split the boxes much more to be able to discard some. In our paper, we discuss add-ons to the presented box subdivision algorithm in order to improve its performance also in these cases. If we fast forward, we can also find a good approximation of the Fermat point, which is colored in blue, for this almost degenerate configuration of cluster points. Given a cluster and an additional point, we can look for all points with the same distance to the cluster. The set of points with the same distance to a given cluster is called an n-ellipse if the cluster has size n. It is a smooth curve unless it passes through a cluster point. In the example, we see a 3-ellipse, which has distance 1.4 to the 3 cluster points. Note that a 2-ellipse is also known as a normal ellipse. Our box approximation algorithm is mainly based on the PV construction by Plantinga and Vector, but it needs some special care if the ellipse passes through a cluster point. Our predicates classify boxes into 3 types: boxes which definitely contain a piece of the ellipse, shown in green, boxes which might contain a piece of the ellipse, shown in orange, and boxes which surely do not contain a piece and can safely be discarded, shown in red. The green and orange boxes satisfy that the gradient of the Fermat distance function does not change a lot within this box. Additionally, green boxes also have at least one corner on each side of the ellipse. In order to derive an approximation with small Hausdorff distance to the real n-ellipse, we further refine all boxes which contain pieces of the ellipse. Here we show the same animation for finding an approximate n-ellipse, but without the underlying boxes. The approximation algorithm for n-ellipses can be adapted to approximate multiple ellipses during the same box subdivision procedure. This can be used to create a contour plot with roughly equally spaced n-ellipses. Here showing the refinement step. Once again, we show the animation without the underlying boxes. Given a cluster, in the example of size 1, and an additional point P, we define the distance between them in the beginning of the video, in the example being roughly 0.5. If we add another cluster, in the example of size 2, we can compare which cluster is closer to the point P. Here, the cluster C1 is closer to P than cluster C2. In this case, we say that P lies in the Voronoi region of C1. We can repeat the same analysis with another point Q. This time, the distance from Q to C1 is bigger than the distance to C2, and therefore we say that Q lies in the Voronoi region of C2. If we classify every point in the plane according to whether it is closer to C1 or C2, we derive the min-sum Voronoi diagram. It is a subdivision of the plane into regions. The region of a cluster or site consists of all the points that are closer to that cluster than to any other cluster. A cluster and its Voronoi region are drawn with different shades of the same color. Again, box subdivision can be used to derive an approximation of the min-sum Voronoi diagram. First, the boxes are split until a PV construction is possible. In a second phase, we further split all boxes which contain pieces of an edge until the approximation has epsilon Hausdorff distance to the min-sum Voronoi diagram. We again show the same animation, but this time without the underlying boxes. The diagram has a couple of interesting properties. First, all the edges are smooth, unless they pass through a cluster point. In the example on the right hand side, the edge between the red and the green region is non-smooth, just right at a red cluster point. Second, only clusters of smallest size can have an unbounded region. This property comes from the fact that the min-sum Voronoi diagram is a generalization of the multiplicatively weighted Voronoi diagram of points. Regarding the size of the diagram, we show two simple worst-case lower bounds, assuming that we have m clusters and n points in total. An omega of n lower bound can be derived by constructing two clusters of n half many points each, all lying on a common circle. The points are equally spaced and alternate between the clusters. In this case, the min-sum Voronoi diagram has linear many faces. An m squared lower bound can be derived by constructing n half many clusters of size 2 each. We arrange the clusters such that the line segment connecting each pair of cluster points forms a grid. In that case, the diagram induces theta of m squared many faces. I want to end with a list of further readings, and thank you for your attention.